Good morning, my fellow scientists. It's Wednesday, February 1st, and I'm here to talk about laser etching. So, as those of you who've been following this little adventure for the last month know, I have been assembling microfluidic devices out of acrylic after laser etching the channels into that acrylic substrate. And yesterday, I got a hold of some substrate and cut a whole bunch of different channels with a whole bunch of different parameters to try to find optimum parameters for good depth. So what I need is something that cuts deep enough to make a channel that won't collapse when I seal the device, but something that cuts shallow enough to make small, controllable channels instead of really deep trenches, or worse, a full through cut. The easiest parameter to change while I'm doing that is the speed of the etch. So you can imagine this like a magnifying glass that you slowly focus a spot from the sun with, and then pull that magnifying glass to focus on different spots slowly. And if you do that, you burn every spot along the way. But if you move fast, you barely heat it up. And somewhere in between, you can control just how much heat you deposit into your ants or wood or what have you. This is the same idea. We're going to take a piece of plastic and blast it with laser light, and if we move very quickly, we just sort of barely scratch it. But if we move slowly, allowing every spot to be continuously blasted for a longer period of time, we get a deep channel. Let's look at the results. Here we see the really fast translation. That channel depth is something like 20 to 50 micrometers, so human hair kind of depth. Now, here we have something where I've only moved it about 30 millimeters per second, and that gives us really deep 200 micron trenches. And those fill with water much more easily, and that's very similar to what I was showing here from a couple weeks ago, where I made very deep channels. So there you have it, the first step toward an optimized protocol for generating microfluidics out of acrylic. I've got an undergraduate helping me with this, for whom I'm very grateful. She's been assembling these devices and testing them and then breaking them in half to look at the cross-sectional area. So far we've discovered that indeed you can make a device out of these things and it doesn't collapse under the sealing conditions. So, pretty exciting. I'm pretty happy about it. Another week of optimization and I think we'll be able to make some devices to make much smaller droplets than we were previously. So stay tuned for more from the Allen Lab in terms of science, actual results, and who knows, maybe some fun discussion of the philosophical ramifications of nanotechnology.